Hello guys, I'm as you guys know, I'm just doing this. If you are watching from, if you have watched the linear algebra, not tutorials, so you know that I'm not doing this doing this as, oh, this is not intended to use as used as a tutorial for your studies or mm, your exams or like that. I just trying to understand the subject material myself and improve my English hopefully. So today I'm going to new subject or new module for my examinations, which is solid state materials. Under that, there is two parts. One part is quantum mechanics. So I'm going to talk about quantum mechanics, and I'm using the book you shown in this picture, the Introduction to Quantum Mechanics, third edition by Griffith, David, and Darrell. I don't. Yeah, yeah. So I'm going to use that book as my reference book. Unfortunately, I can't show you the book because of copyright issues. So I have a book in my hands. I'm going to do my best to explain this to actually myself. But hopefully, if someone is watching who need to understand the material also can follow along. But I'm not recommending it. Maybe in the future I will do tutorials, but for the time being I'm just doing not tutorials, right? So keep that in mind, and I'm doing this to improve my English also. So first I'm going to talk about is first topic uh, in consideration is, I'm going to delete this, is wave function, the wave function. So what is wave function? So first I'm going to this is the chapter 1 of this book, and first section is I'm going to talk about is today this video's topic is the Schrodinger's equation. The Schrodinger's equation. I'm going to talk about a little bit about what is Schrödinger equation. First, let's get a reminder how we did physics in our A levels and in high school. So basically, what we used, the main physics we used is Newtonian mechanics, right? Newtonian physics, no, Newtonian mechanics, which is basically based on three laws. First law, second law, and third law. Very convenient way of naming laws. So first law is, if object is not experiencing any force, it will stay rest or will move in a linear path at constant velocity. Second law is uh, the rate of change of momentum experienced by a force is equal to the force act on that object. Third one is every force has an equivalent uh, has a reaction which is equivalent in magnitude and opposite in the direction. That are the three laws Newtonian mechanics is based on, and we use force, and the notion of force is based on those laws, and we use them to calculate and predict motion of objects in our day-to-day life. For example, let's say and another point is these are laws, so there are no proving of these are not theorems, these are laws. So there are no proving them, we use them as grounded, and we they are proved using only experimental results, like that. No like that, as to my knowledge, but maybe I'm wrong, you can correct me. This is my understanding, and yeah, for the record, I'm not giving any what do you call, I'm telling things in this recording which I believe is true, that that might actually not be the case. So if I'm mistakes take do a mistake on something explaining, or yeah, something like that, you can place a comment, let me know, right? Okay, Newtonian mechanics. So if I take object, let's say uh, this is a rod. I'm going to change my pen. Yeah, this is a rod. I can't draw a straight line, man. Yeah, let's try best my best. Yeah, that's pretty good. There's a rod. There's a vehicle moving in this direction. And let's say this is the position we take, x equals 0, and we measure x, which is the distance from the origin to the object. If it has mass m, uh, we to describe any parameter, like velocity, momentum, kinetic energy, something like that, any variable of interest, we first need to find the function xt. This xt function, which is the uh, position of this object uh, at any given time. This is a function of t. We need to find that. So to find that, so if we know this x, the function of position of this object as a function of time, we can deduce other parameters, such as if we want to find velocity, we know velocity is dx dt, the rate of change of the position. Or if we want to find momentum, we can use mv, which means m times dx over dt, the first derivative of x. If you want kinetic energy, let's say t, or let's say ek kinetic energy, it is half mv square, right? uh, so if we know that, since we know v as a function of x, we can write this as dx over dt square. So we can take any if we know this position function, we can derive uh, any what you call any other uh, motion properties, no, any other parameters related to motion of this object can be derived using that function. So to do find this function, we simply use Newton's second law, which is F equals, sorry, which is F equals ma, second law of Newton's second law of motion, which says, so we know a is the derivative of v, first derivative of v, so we can write this as dv over dt, or we can write this as the second derivative of x respect to time. So we apply this equation. I'm going to write as a differential equation f equals m times dx, or dx second derivative of x respect to t. So to solve this, we need to find f, right, first. So let's, we don't know f, what is f yet. So for a moment, let's assume this is this object, what do you call this vehicle in a field, force field, right? So if it in a field, let's say, which is field is vx, mm, yeah, let's say it's a v of x, let's say this is y, or time, or can be any other lot of there can be lot of variables that changes this VO potential function of this field, which is a potential function of the field where the object or the vehicle moves. So we know from Newtonian mechanics or the classical mechanics, we know f equals a partial derivative of v respect to x. The change of what do you call rate of change with respect to x of the potential function is equal to the force. If we write this as if we write this if we combine these two equations, we get partial derivative of v over x minus the minus sign is to denote the sign convention, which means yeah, just a sign convention thing. We don't have to worry about that. If you want to uh, if you don't need to know what the negative sign does, you may follow a classical physics tutorial about fields, or especially if you want gravitational field or electric fields, you will to come to understand why there is a negative sign. It is for beyond the scope of this uh, section, so I'm not going go into in detail about it. So we can write this as combining these two, dx squared dt squared, right? D squared x over dt squared. So we this is the second law, uh, Newton's second law, right? Second law. But to this to be true, I forgot to mention that this equation is only true uh, when the potential function or the energy field the object is moving is a conservative field, or it's only work if a conservative field. Luckily enough very fortunate for us, every microscopic uh, microscopic fields are always conservative. It's very convenient for us for future things, so that's why we use this conservative conservative. So no one knows. So there are explanations why this is true, this equation, but no one understood why when it was first introduced by Newton. I'm saying so much, right? So yeah, again I did that. I need to avoid that. Uh, I cannot. Okay. Yeah. So F equals ma is an equation which Newton introduced, but we don't know how it worked until far more far later. But we can uh, we can use that equation to calculate everything, right? For example, we can if you know the position force and mn acceleration, we can almost get, almost get any property of that moving object uh, related to kinematics of that particle object. So yeah, this is the Newton's second law, but this law does not work on microscopic or macroscopic. So no, works on only macroscopic level, doesn't work on microscopic level. Microscopic level. Two no, doesn't work on microscopic level. Then there's another equation. I'm going to change the colors. There's another equation called Schrodinger's Schrodinger's equation. Schrodinger's equation, which uh, says the moment of microscopic objects in their relative level, a microscopic level. First, first I said, two, we use Newtonian mechanics, and if we know the position function of the object, we can obtain any proper variable, dynamic variable we are interested in. Similarly, in microscopic level, the object doesn't have a exact position, as some experiments suggest. We talk about them in later videos. So what the equation, first I'm going to write the equation, then I'm going to explain. uh, then I'm going to explain. First one, the equation of Schrodinger equation is I h cross or h bar. I think, I don't know what is the exact name for that symbol, which simply means, we know h is Planck's constant or Planck's constant. I don't know how to pronounce this correctly. Planck's constant, which is Planck constant. Then h bar is just reduced Planck constant, is just h of 25, which is reduced Planck's constant. Which is a partial derivative of psi. This is later I'm going to little bit talk. This is the main thing we study in this section, which is the wave function, which denoted as psi. I'm going to use capital psi. Capital psi is this, and I'm going to use simple psi as like this. Respect to t equals minus h cross square over 2m times uh, partial derivative of psi with respect to x plus v of psi. This is the Schrodinger's equation. This equation called Schrödinger is as previously we talk about Newton's second law of Newton's second law. This is this is exactly like that, not in the mathematical term in sense. It means we use this to uh, find this equation. We use this equation to find this wave function. Wave function. For a macroscopic object, we use position function, but in microscopic level, we need to use wave function, which is a function of time, the position and also time. We know the weird thing about this is, when you're talking about position function of a macroscopic object, we know what is physically means, right? So if you say it's when we say it's position function, which means we know it, the function is saying the physical location of that object in the real world, or uh, in the frame of the reference frame we are talking about. It's a physical thing, we can measure it. But the wave function, which is a function of time and also the position, is not something we can measure. It's just a purely mathematical construct we use to determine certain properties and behavior of materials, but we don't know what it is, but it works, right? So we don't know how it works, but we know it works. It's something like, if you are driving a car, let's say you are not that tech savvy, or uh, enthusiastic person about cars, but you know just how to drive the car, right? So you know if you turn your steering wheel, car is going to change direction and turn. To do that, to drive a car using steering wheel, you don't have to know how the internal mechanism of the steering wheel works, or how the engine works, or you don't need to learn any of that. You just know that if you turn the steering wheel, car is going to turn. It's something like that. It is same as with the Schrödinger equation. N- uh, till the time of I'm speaking, until the time of I'm speaking, no one is no one have ever explained why Schrodinger's the wave function, what is wave function, why, how it's work. No one knows. uh, no one knows yet. Maybe in future someone will explain it, but no one until now no one knows. But we know how it's work, so we can use it to our advantage to do our calculation, but no one knows why it works, what it is, what it represents. No one is knows. But there are some interpretations. So since we don't know how it works or how what it is, scientists have came up with various interpretation for this wave function. There are a lot of interpretations. In this chapter we mainly focus about the statistical interpretation or Bose interpretation, where which is going to I'm going to talk about in next chapter. So yeah, that's the thing. Mm, so we don't know what it is, but we know the wave function behaves this Schrodinger obeys this Schrodinger equation. We can use them to determine the wave function. Using wave function, we can predict different properties or different things about microscopic objects. Uh, that's the main idea of the Schrodinger's equation, right? No, there's no yet we don't know all these terms mean. If I'm if I can explain simply, this is I, which is square root of -1, which is this is h cross or h bar, which is reduced Planck constant, and m is mass of the object, I think. Um, then psi is this is psi, Greek letter psi. Uh, I don't know how to write it. I think this is psi, capital capital. This I'm going to write capital psi as this and simple psi as this. So to distinguish between both. Uh, these two has different meaning in quantum mechanics. This is Schrodinger's this is wave function. This is time independent wave function or something like that. So in this equation we have what you call the capital psi. Okay. So for time being, don't worry about what this equation means or what is the wave function is, anything like that. Just it's a way of finding properties of some particular object given the wave function, similar as the position function of a macroscopic object. If we have a position function of macroscopic object, we can identify various type of dynamic variables of that object. Similarly, if we know a wave function of microscopic objects such as electron, photon, or maybe neutron, maybe a proton, something like that, we can predict some its properties using that equation. It's the same idea, but as no one knew, no one, let me especially no one knew how second law of Newton's work, but everyone understand why understand how we not how it works, how we can use that to our advantage and predict motion of a macroscopic object. We are going to do the same for the Schrodinger equation. Then maybe hopefully we can use some interpretations like statistical interpretation of quantum mechanics or Schrodinger's wave function or some other thing to get an idea or feeling about what this all means. Yeah, that's about it. In next video, we're going to talk about the statistical interpretation of quantum mechanics or wave function. Uh, yeah, so thanks for watching. See you in the next one.